Hello, in this class we can discuss symmetric and antisymmetric wave functions once more. Okay, so let us start with the antisymmetric wave functions. An antisymmetric wave function can be written in the form of a Slater determinant. So that is psi A. Psi A is equal to a constant A times u1 of 1 or q1. Q1 is the arguments of the first particle. U okay, u1 of q2 argument of the second particle, u1 of q3 etc. to u1 of qn, or you can simply put 1 2 3 etc. So, u2 of q1, u2 of q2, u2 of q3 up to u2 of qn. So this so similarly u3 of q1, u3 of q2, u3 of q3 okay. So it goes like this up to un, up to maybe un of q1, un q2, un of qn. Okay. So this is the antisymmetric wave function. Now let us assume, so we have discussed already this thing in the last class. So let us assume there is a interchange of arguments of the first and second particle. Okay. So when we interchange a pair of particle, then what happens? The respective columns get interchanged. This column comes here and this column goes here. So what happens? So this psi A become minus psi A. Okay. So if you change a pair of particle, then this get negative sign. If you change two pairs, or if we effect two permutations, then it will psi A again become psi A. Okay, so such wave functions are called antisymmetric wave function. Okay. Antisymmetric wave functions. Now, okay, if two or more particles are in the same single particle state, okay, that means the corresponding rows. So here u1 is the first single particle state, u2 is the second single particle state. If two particles are in the same state, then u1 and this u1 row and u2 row are identical. So that means this is u1 of q1, u1 of q2, u1 of q3 etc, u1 of qn, and this also u1 of q1, u2 of u1 of q2, u1 of q3 etc, u1 of qn. So this the corresponding, if the first and second single particle state are the same, then this thing is these two are identical. So you know, in a determinant, if two rows or two columns are identical, then that determinant is 0. Okay, so That is, if two or more particles are in the same single particle state, then the corresponding determinant become 0. That is, psi a is equal to 0. That means the such a state is impossible to realize. So അങ്ങനെയുള്ള ഒരു സ്റ്റേറ്റ് ഉണ്ടാവില്ല. Suppose antisymmetric wave function ആണെന്നുണ്ടെങ്കിൽ we cannot have, if the system is described by an antisymmetric wave function, so it is impossible to have two or more particles in the same state. Okay. Then the particle of the system must all be in different states. This is equivalent to Pauli's exclusion principle. Okay. That is, we can say in conversely, we can say like this. So if the systems, see, if the antisymmetric wave function is the wave function describing the system of particles, then it must all the particles in the system must be in different state. Okay. So conversely, we can say, തിരിച്ച് നമുക്ക് പറയാൻ പറ്റും എങ്ങനെയാ, if the statistical system composed of particles obeying an exclusion principle must be described by a wave function that is antisymmetric in its argument. So the statistics of the particles obeying exclusion principle are called Fermi-Dirac statistics. Dirac statistics. Okay. Or simply Fermi statistics. Fermi statistics. Okay. So such particles are called fermions. So these particles obeying Fermi-Dirac statistics are referred to as fermions. Okay. So fermions. Now let us go back to the statistical weight factor. Statistical weight factor quantum. Now we have two kinds of quantum statistics. One is the statistics obeying a symmetric, or statistics of a symmetric statistics with a symmetric wave function. So we can write it in this way. Now W, so symmetric and antisymmetric wave function. Statistics with the symmetric wave function, and okay. Now the statistical weight factor W FD, that is of the particles obeying Fermi-Dirac statistics, that is obeying exclusion principle, or described by antisymmetric wave function, then the statistical weight factor is equal to 1. Okay. If the number of particles Ni in the distribution set is equal to 0 or 1. എന്ന് പറഞ്ഞാൽ മാക്സിമം ഒക്യുപ്പേഷൻ ഇസ് 1. ഓരോ സ്റ്റേറ്റിലും 0 പാർട്ടിക്കിൾ അല്ലെങ്കിൽ 1 പാർട്ടിക്കിൾ, ഒരിക്കലും 1ന് കൂടാൻ പാടില്ല. അങ്ങനെയാണെന്നുണ്ടെങ്കിൽ weight factor of the distribution set Ni is equal to F. We can write it in this way. Is equal. Now if it is more than that, Ni is greater than 1, then it is equal to 0. That distribution does not occur. Okay. So അതാണ് പറയുന്നത്. അപ്പോൾ ഇപ്പോൾ ടോട്ടൽ എൻ പാർട്ടിക്കിൾസ് ആണെന്നുണ്ടെങ്കിൽ ടോട്ടൽ എൻ പാർട്ടിക്കിൾസ് ആണ് വി നോ ദാറ്റ് സിഗ്മ എൻ ഐ ഇസ് ഇക്വൽ ടു എൻ. അപ്പോൾ ഈ സിഗ്മ എൻ ഐ വാട്ട് ഇസ് സിഗ്മ എൻ ഐ? ഇപ്പോൾ നമ്മുടെ ഡിസ്ട്രിബ്യൂഷൻ സെറ്റിൽ ഒന്നാമത്തെ സെറ്റിൽ 0, രണ്ടാമത്തെ സെറ്റിൽ 0, മൂന്നാമത്തെ സെറ്റിൽ 1, സോറി 1 1 1, മേ ബി ഇൻ സെക്കൻഡ് നെക്സ്റ്റ് energy level it is 0. This is okay, all 1 or 0 is fine, but 1 2 0 3 etc, this is not possible. Okay, this is not possible, this is fine. Okay, so ഇത് possible അല്ല എന്ന് പറയുമ്പോൾ നമ്മൾ weight factor is 0, this weight factor is 1, currently 1. Okay, so that's the thing. Now let us discuss about the symmetric wave function. Symmetric wave function. In the case of symmetric wave function, this restriction is not there. We cannot have ഒരു സിംഗിൾ പെർമ്യൂട്ടേഷൻ കൊണ്ട് വേവ് ഫംഗ്ഷൻ നെഗറ്റീവ് ആവില്ല. പെർമ്യൂട്ടേഷൻ ചെയ്ത് കഴിഞ്ഞാലും പി സൈ ഇസ് ഇക്വൽ ടു എന്താണ്? സൈ തന്നെയാണ്. എത്ര നമ്പർ ഓഫ് പെർമ്യൂട്ടേഷൻസ് എടുത്തു കഴിഞ്ഞാലും വി ആർ ഗെറ്റിംഗ് ദ സെയിം വേവ് ഫംഗ്ഷൻ. അപ്പോൾ സച്ച് വേവ് ഫംഗ്ഷൻസ് ആർ കോൾഡ് സിമെട്രിക് വേവ് ഫംഗ്ഷൻ. ഇതിനെ നമുക്ക് ഡിറ്റർമിനൻ്റ് ആയിട്ട് ചെയ്യാൻ പറ്റില്ല. ഡിറ്റർമിനൻ്റ് ആയിട്ട് ചെയ്യുമ്പോൾ നമ്മൾ ആൾട്ടർനേറ്റീവ് ആയിട്ട് വരുന്ന ടേം നെഗറ്റീവ് പോസിറ്റീവ് ആവുമെന്ന് നമുക്കറിയാം. സോ ഇപ്പോൾ നമ്മൾ എന്ത് ചെയ്യുന്നു, ഒരു കോളം ഇൻ്റർചേഞ്ച് ചെയ്ത് എന്ന് പറഞ്ഞാൽ പാർട്ടിക്കിൾസിൻ്റെ പൊസിഷൻ ഇൻ്റർചേഞ്ച് ചെയ്തു, പാർട്ടിക്കിൾസിൻ്റെ കോർഡിനേറ്റ്സ് ഇൻ്റർചേഞ്ച് ചെയ്ത് കഴിഞ്ഞാൽ you will get the negative value of the determinant. Such wave functions are called antisymmetric wave function. ഇവിടെ ഇന്റർചേഞ്ച് ചെയ്ത് കഴിഞ്ഞുകൊണ്ട് വേവ് ഫംഗ്ഷൻ മാറില്ല. അപ്പോൾ അതുകൊണ്ട് ഇവിടെ we cannot represent the symmetric wave function as a Slater determinant. Okay, so the statistical or this statistics obeying such particles are called Bose Einstein statistics. Bose Einstein statistics. Einstein statistics or simply Bose statistics. So such particles obeying the Bose Einstein statistics or described by symmetric wave functions are called such particles described by symmetric wave functions are called bosons. Okay, so bosons. Okay. Now the statistical weight factor WBE of Ni is equal to 1 for all Ni values. Okay, or for Ni, for all Ni. That means whatever Ni value may be, the statistical weight factor for any distribution set is equal to 1. Okay, statistics are governing a particular particle, species of particle, and the intrinsic spin of the particle. These two have an intimate relationship or intimate connection. Okay, so that is, or if the particle with an integral spin, that means in unit of h cross, 1h cross, 2h cross, 3h cross, they obey Bose Einstein statistics. Bose Einstein statistics. Okay, now if the particles are with a odd half integral, that means half h cross, 3 by 2 h cross, 5 divided by 2 h cross, etc. So such particles obey Fermi-Dirac statistics. Fermi-Dirac statistics. So there is an intimate connection between the statistics of particle and the spin of the particle. If they are, if the particle have integral spin, then they obey Bose Einstein statistics. And if odd half integral, that means half integral 3 by 2 integral, 3 by 2 h cross, 5 by 2 h cross, 7 by 2 h cross, etc. So such particles obey Fermi-Dirac statistics. So for example, here example for Bose Einstein particles, BE particles are, or bosons are photons, photons, phonons, then pi mesons, etc. Okay, gravitons, etc. Next, fermions, that is FT particles, Fermi-Dirac particles, or fermions are electrons, protons, sorry, protons. Okay, then neutrinos, etc. Okay, so these are Bose Einstein and Fermi-Dirac particles. Okay. So you can summarize it as follows. So first, symmetric, symmetric wave function, antisymmetric wave function, antisymmetric wave function, symmetric wave function. So such do not do not obey exclusion principle. No need to have an exclusion principle. Then here obeys an exclusion principle. No two particles can occupy a single particle state. Then they obey Fermi, sorry, Bose Einstein statistics, and they obey Fermi-Dirac statistics. Okay, then so the particles are called bosons, and this particle, the particle obeying FT statistics are called fermions, and they have integral spin. Okay, the unit of h cross. Okay, so here odd half integral. Okay, so n h by 2, where n is 1, 3, 5, etc. Okay, so these are called, this is the symmetric wave function and antisymmetric wave function. Thank you.